Harmonic oscillators seem to pop up everywhere in physics, and they have a very special place in quantum mechanics as well. In this video, we'll take a detailed look at the energy states of a single particle harmonic oscillator. We'll solve the stationary state Schrödinger equation and also try to understand why the energy states of such a system must be quantized. Let's get to it. As you may know, a harmonic oscillator is just a system that is being acted upon by a force, F is equal to minus kx. Let's find an expression for the potential for such a system. We'll use the relation between force and the potential given by F equals to negative derivative of potential with respect to x. This gives us that the potential V is equal to the negative integral of f dx, which we can calculate to be 1/2 kx squared. Let's write this in a different form by introducing a constant omega squared equals k over m, where m is the mass of the particle. Thus, V of x can be written as follows. Now let's talk about quantum mechanics. Our goal for this video is to find the different energy states that are permissible for a particle in a harmonic potential. For this, we'll use the measurement postulate of the quantum mechanics, which tells us that the only energy values that a particle can have are those that satisfy the eigenvalue relation H psi is equal to E psi. This is also known as the time-independent Schrödinger equation. Here, E represents the possible measurable energy states, which is what we are after, and H is the Hamilton operator. It is given by minus h power squared over 2m multiplied by the second derivative plus the potential. Using the expression for the potential of the harmonic oscillator, the Hamiltonian for this problem becomes. So the time-independent Schrödinger equation for the harmonic oscillator problem is as follows. Now let's go to our notepad and see how we can solve this. So let's try to think about how we can go about solving this equation over here. Remember that we are trying to solve for this E right over here. That's our goal. And moving forward, our approach will be to take this equation and we'll introduce a few new quantities and we'll scale it in order to make this simpler. And then we'll examine the properties of this equation intuitively and see if that can give us any insights about how we can solve this. Anyway, moving forward, what we are going to do is take this equation and divide it by 1/2 h bar omega. We are doing this because this is just something which will simplify our equation later. So this right side, this would reduce to an expression like this, where I have also pulled out the psi, and our right side, it would just be 2e over h bar omega psi. Okay, so this is what we get after dividing by 1/2 h bar omega. Now let's introduce a few new quantities over here. So we will let's introduce a q, which is equal to x over the square root of h bar over m omega. and we'll introduce an epsilon is equal to E into over h bar omega. You'll notice that this epsilon is just this term over here, and if you look closely, you'll also realize that this q is the square root of this term over here. So we can just take that quickly. So if we try to figure out q squared, it would be x squared over h bar into m omega, which is nothing but this term over here. So we will use that to rewrite our equation as minus h bar m omega second derivative with respect to x plus this term we'll write as q squared and psi over there, and this is just equal to epsilon psi. Okay, now I claim that this term over here is equal to minus d squared over d q squared. Let's take a look at that. So if you try to find d psi dq, let's try to do that. Now psi is a function of x and not as a function of q. So we'll have to use the chain rule. So this can be written as d psi dx into dx dq. Now in this equation over here, if we take this constant term, the square root, and move it to the other side, we'll get an equation where we have isolated the x, and then we can find dx dq. And since this expression for x would then be linear in q, the derivative would just be this constant term over here. So this is just the root of h bar over m omega. Let's try to find the second derivative of psi dq of d psi dq. So again, we'll have to use the chain rule. Now this would just equal d dx into d psi dq dx dq. Here we have just done the same thing, just instead of psi we have d psi dq. So now inserting this expression for d psi dq which we found above, we get d dx of square root of h bar over m omega into d psi dx into dx dq. This is the same as this term, which we found to be just this constant over here. So this is the square root of h bar over m omega. Taking out the constant, and we see that this is derivative with respect to x, derivative with respect to x, and then these two constants are the same, so this will just equal to h bar over m omega, and the second derivative of psi with respect to x. So here we started out with second derivative of psi with respect to q, and that is just equal to this term, which is what we are claiming. Okay, so this term can be written in terms of second derivative of q, and we'll just rewrite the rest of the equation here. And that should be equal to epsilon psi. So now we'll write this equation in a different form. What we'll do is we'll multiply through by -1 and then move this term to the left side, which gives us second derivative of q and then plus epsilon minus q squared. This is our operator, and then we have psi is equal to 0. This equation we'll call equation 1. Now let's look at equation 1 divided by q squared. This is just 1 over q squared d squared dq squared and then in addition to divided by q squared, I will also move this term over to the right side again. So that would give us 1 minus epsilon over q squared psi. Now the reason we did that is because we want to see what happens as q goes to infinity. So we want to see how this equation behaves for large values of q. So when q is big, q squared is big, therefore epsilon over q will be small. So the right side would tend towards psi. So now we have established a relation between the second derivative of the wave function and the wave function itself. So when we have a relation between a function and its derivative, this should automatically get us thinking about the exponential functions. We know that exponential functions are such functions where there is a clear relation between the function and its derivative. So a reasonable thing to do at this point would be to try out different values for psi of q. We would try e raised to aq, one may try e raised to a q squared, and other such exponential functions. Insert them into this differential equation and see what we get. After some trial and error, you'd quickly stumble upon this function, e raised to minus 1/2 q squared. Now, if you insert it into this equation over here, what you'd get is the following. So, after inserting psi into this function, we see that this function is indeed satisfied. With epsilon being 1, psi of q is equal to e raised to minus 1/2 q squared is actually the exact solution to this function. Again, if epsilon is 1. So, this means that we can conclude that psi of q behaves like e raised to minus 1/2 q squared for big values of q. But what would happen for small values of q? To look at that, we'll assume that psi has the form v of q, where v is some function, and moving forward, we'll explore its properties. Psi has the form v of q into e raised to minus 1/2 q squared. Now, inserting this into equation 1, this equation, that would yield an expression like this. So I will just fast forward through that part. So after some algebra, this equation is what we get. Now, this equation places a constraint on what v can be. Our v has to satisfy this equation over here. So we'll call this equation 3. Anyway, moving on, we will assume that our v of q can be written as a power series. So it can be written in the following form. The sum up to infinity of k is equal to 0 of ak x to the power of k. Now what we'll do is we'll take this form of v and put it into equation 3. For that, we'll have to find out what v derivative is and what the second derivative of v is. So if we try to find what v derivative of q is, we would get something like this. And if we calculate the second derivative of v, we would get something like this. But here we can adjust our index a little bit. This sum can equivalently be written as the sum from k equals to 0 to infinity of k plus 2 into k plus 1 a k plus 2 into x raised to k. You will see that these are equivalent, first of all, if you write out both of them. And secondly, notice that the reason we are doing this is because when k is equal to 0, well then this k is 0, and then the entire thing is 0. When k is equal to 1, then this term is 0. So then again, this entire thing is 1. So here we have just incremented 2 to our k's everywhere. So that's why these two sums are equivalent. So with this in mind, we have both v prime and v double prime. If we put this into equation 3, we would get something like this. So here I also realized that I wrote these series in terms of x when they should be in terms of q, because q is our dependent variable. So let's just fix that over here. Okay, so if we simplify this a little bit, this sum can be written as the following. So this is what we would get. Now, this implies that each of the terms must be equal to 0 individually, because we have these powers of q. Therefore, each such power of q must be equal to 0. So we have that this part over here is equal to 0. So let's write that down. So this is what we would get. Now, if we try to solve for ak plus 2, what we would get is ak plus 2 is equal to. So what we have here is that ak plus 2 is related and based upon the value of ak. So this is a recurrence relation, which we will call equation 4. Now, it's easy to get lost in the mathematics of it, but let's try to keep track of what we are doing. So if we back up a little bit, what we found is that it's reasonable to say that psi has this form over here. It's some function v into e raised to minus 1/2 q squared. This exponential term, because we found that psi has this form for big values of q. Then inserting this into our simplified time-independent Schrodinger equation, we got this constraint over here. And then assuming that v can be written as a power series and inserting it into our equation 3, we found what the coefficients have to be in this power series. So what we have found is the relation of these coefficients over here. Now, there's something I would like you to notice, and that is, let's see what happens when we take the limit as k goes to infinity of a k plus 2 over a k. Now, that would be approximately equal to 2k over k squared, because multiplying these two together will lead to a k squared term. So we just have k squared, And also this constant over here doesn't matter in the limit. So this would just equal to 2 over k. Now notice also that the function e raised to x squared has the following Taylor series. So this is the Taylor series of e raised to x squared. Now for this, we also find that if we take ak plus 2 over ak plus 2 over ak, after some calculation, we'd say that this is just equal to 1/2 k factorial over 1/2 k plus 2 factorial. There. Which would just simplify to 1 over 1/2 k plus 1, which for big K is just 2 over k. So from that, we saw that in the limit as k goes to infinity, the ratio between the coefficients for these two functions, for our v of q and this function e raised to q squared, it's the same, which means that for big Q's, we have that v of q acts like e raised to q squared. Now, this is really a problem because what we said is that we assume that psi of q was going to be v of q into e raised to minus 1/2 q squared. So if v of q is going to behave like e raised to q squared, then psi of q would be e raised to half q squared. But this is a function that diverges for big values of q. And that is a problem because then our wave function isn't normalizable. Remember that a wave function is said to be normalizable if it is square integrable, so that this integral over here has to be finite. If it's infinite, then it is not normalizable, and this function, it's not normalizable. So the only way this can work out is if this recurrent series breaks off at some point. What this means is that, well, let's write down this recurrent series down here. We had that a k plus 2 is equal to k plus 1 minus epsilon over k plus 2 into k plus 1 a k. So this series has to break off. what that means is that there must exist an index an which is equal to 0. Because what would happen is that if an is 0, then an plus 2 would be 0, and then an plus 4 would be 0, and so on. So all the terms after that would be 0. Okay, let's think about what this tells us. Now, suppose that an is equal to 0, but an is the first term, which is 0. Or, okay, we can make it simpler by saying that an plus 2 is the first term, plus 2 is the first term, which is equal to 0. So what we would get is that an plus 2 is equal to, write it out using this recurrence relation, 2n plus 1 minus epsilon over n plus 2 into n plus 1. an is equal to 0. Because we said that an plus 2 is the first term, which is 0. Therefore, we can set it to 0. And also, we know that an, this is not equal to 0. Because n plus 2 is the first term, which is 0. So then, we must have that 2n plus 1 minus epsilon over n plus 2 n plus 1 is equal to 0. Now, this implies that epsilon is equal to 2n plus 1. But let's remember what epsilon was. Epsilon was a constant that we introduced to represent the value e over 1/2 h bar omega. That's equal to 2n plus 1. And this finally gives us the energy eigenvalues for the harmonic oscillator, which is n plus half h bar omega. So this is our final result for n whole numbers, including 0. Now, notice that these energy values, they are quantized. And let's take a look at why this quantization came about. So, the reason we have this quantization is, well, first of all, due to this recurrence relation. And this recurrence relation came about due to us assuming that V of Q can be written as a power series. But then also, because of the fact that this series has to break off at some point to allow the normalization of the wave function.